Welcome everyone to this webinar on cooling performance optimization of electric vehicle batteries. Thank you very much for joining us today. My name is Paul Lethbridge and I'm the Director of Product Marketing here at SimScale, and I will be your moderator today. Today's presenter, I'm very pleased to introduce Steve Lanay, Application Engineering Manager at SimScale. Steve has a degree in mechanical engineering and a PhD in materials science. Before joining SimScale, Steve worked in aerospace design and engineering simulation. So let's take a look at the agenda for today. So we have 30 minutes today. We're going to tell you a little bit about SimScale and cloud native engineering simulation. And then we're going to get into the live demo. And after that live demo, we'll answer your questions and then explain how to get started with SimScale. What I'd like to do is draw your attention to the panel on the GoToWebinar panel. You can actually ask your questions there, and also encourage you to use the chat as well. So just say hello and submit your questions there. Okay, so with that, I'll hand over to Steve.
Great, thank you, Paul. So first of all, let's have a quick introduction to SimScale. So who are we? Well, we were founded in 2012. We have our head office in Munich, but we have a global presence with 110 employees across 8 time zones. And there's currently millions of simulation jobs being run in SimScale, and we're funded, so we're going to be here to stay. And why would you use SimScale? Well, compared to the traditional systems, SimScale makes high fidelity engineering simulation technically and economically accessible at any scale in the cloud. You can simulate early in the design process when the cost of change is low, and you can simulate more with SimScale without having to have a software and hardware footprint that you have to maintain and purchase. By simulating earlier in the design process, you can experiment with different designs. Traditional simulation tools are used later in the design process to validate a design. But with SimScale being so accessible, being fully cloud-based, any engineers in the design team can easily run their simulations at an early stage to make the most of their designs. Okay, so with that brief introduction to SimScale, let's have a look at what you've all come for today, the demonstration of a cold plate design. So this cold plate that we're going to be looking at is a cold plate for cooling a series of electric batteries. And essentially, we're looking to maximize the thermal efficiency of this design. And we're looking here at a stage 1 design, a version 1 tried and tested design that has been used by an engineering firm to cool their battery packs. But there's a design engineer looking at an early stage version 2 concept. And the designer wants to perform a quick study to understand the thermal performance of this new V2 design. So on the left-hand side of the screen, you can see the original cold plate. This was designed using the traditional best practices from the previous experience in the organization, and they went for a single serpentine cooling channel. However, in the testing, it was found that there were some hotspots on the plate, and there's been some issues with battery longevity. So the designer has come up with something, and this is purely something that they've theorized, and they've gone with a labyrinth system cooling channel in the version 2 design on the right-hand side of the screen. But this is all just imagined by them. They've seen something similar. They've designed it in their CAD package, but they haven't actually had a chance to simulate it yet. So that's what we're going to have a look at. If you've got 2 designs like this, how can you quickly and easily assess the new design at an early stage to understand the performance of it? Okay, so let's jump into SimScale and have a look at how we would do this. So you should be able to see a Google browser on my screen now. I always like to start demos from a Google browser and go straight to SimScale, just to emphasize the fact that SimScale is fully cloud-based. All you need to access SimScale is a web browser. So here I've accessed simscale.com. I already have an account. If you don't have an account, you can create one here. And then I can access my dashboard. So essentially with SimScale, you get a basic SPDM system out of the box. All of your simulations are managed here in the dashboard. You can flick through and see previous simulations that you've run. And you've got full history of the latest jobs that you've been running and the number of core hours that you've got on your account. Obviously, we can search in here as well. So today we're looking for a cooling plate, and I can see here I've got a couple of cooling plate projects. So we're going to open this one up to have a look at it. So this opens the cooling plate project in SimScale, and we can see here that I've got a few geometries. I've got the version 1 geometry where we can see this traditional serpentine cooling channel. And I've also got the version 2 geometry in here as well. So it's a cooling plate with an inlet and outlet and an internal flow volume for the cooling channel itself. And here I've run a series of simulations, and I'm going to have a look first with you at some conjugate heat transfer simulations that we've run on this to understand the thermal performance. So how well can this cooling plate extract heat from the batteries? So in order to set up this simulation, I just had to import the geometry. The contacts were automatically detected, define the fluids and the solids that we've got here. So aluminium for the block and water for the cooling channel, and then some boundary conditions for the inlets, the outlets, and the heat created from a power source, which is the battery. So let's have a look at the simulation result that we get out of here. So with SimScale, everything is done here in the browser. We can pre-process and post-process everything in here. We don't have to go out to another application. We can also create the edits to the CAD geometry directly in SimScale. So after this, I'll show you a simulation from the start where we'll bring the CAD in. But first of all, let's have a look at how these two designs compare to each other. So on the left-hand side of the screen, you can see version 1 of this cooling plate. And on the right-hand side of the screen, you can see version 2. So maybe it's not necessarily so surprising that we've got some high temperature profiles in this design that the design engineer has come up with. We can see the inlets. So we've got the inlet at the bottom, the outlet at the top. And then we're viewing the temperature profile. So we can see the red areas are hot areas, so about 27 degrees Celsius, and the blue areas are down at about 18 degrees Celsius. So we can see with the original design, just after the inlet, the cooling is very effective, but then we've got some relatively high hot spots, around 23 degrees Celsius between the cooling channels. If we look at version 2 of the design on the right-hand side, it looks pretty dreadful actually. We've got some relatively well-cooled regions, but then we've got very high temperature regions in the top left-hand side of the cooling plate. So from an initial thermal performance point of view, it doesn't look as good. And if we have a look on the backside here where we've got a cutting plane, we can see the actual flow channels so that we can try and understand what's actually happening. So we can see the inlet coming in. Here now we've got the coloring in velocity. So we can see that we've got some high velocity regions, maybe up to sort of 5 meters per second. And then version 1 of the design maintains a relatively consistent velocity other than some peak velocities at the corners of around 4 meters, 3 to 4 meters per second. On the version 2 design, we can quite quickly see what the problem is here, because we've got the same sort of inlet velocity coming in, but then we've got very low velocities in these channels further down the flow. So we've got almost zero velocity, stagnant flow. So that's why our cooling channels aren't effectively removing heat from the batteries in that area. So we could obviously aid the visualization of this by adding some vectors to these plots to understand where the high and low velocity regions are. So we can see that we've got no flow velocities in this region. Okay, so that's the post-processing of those two designs from a thermal point of view. But the other thing that we might want to do here is consider the flow in isolation, so that we can understand things like the pressure drop and understand how this design is performing. So I'll just exit the comparison there and have a look at one of the other simulations that we've run here for the actual flow velocity. So we've taken purely the fluid volume here, and we're analyzing this in isolation so that we can understand and optimize for the pressure drop that we've got in here. So we can see the pressure throughout the system, and obviously the crucial thing that we would want to get out of this is what is the pressure drop, because we want to minimize the pressure drop that we've got in the system in order to have the most efficient system, to have the lowest pump driving force to pump the fluid through these cooling channels. So we can make use of cutting planes and statistical analysis to obtain what the pressure drop is, so about 280 kilopascals. And this is being taken at a cutting plane that's slightly back from the union joint, just so that we've got the actual pressure drop in the channel rather than taking that connector into account. But of course, rather than coming directly into the post-processor, we can get these things out of the result control items as well. So we could look at the pressure difference. So you can see we've got a nicely converged pressure difference at the inlet and the outlet of 292 kilopascals. So this one isn't taking the pipe joint into account. It's actually at the inlet and the outlet. And we could also look at the pressure drop from the inlet and the outlet if we haven't set up a specific control. Okay, so so far I've shown you simulations that have already been run, but obviously we want to have a look at how we would set up one of these simulations from the start, making use of a simulation that has already been set up and configured here. So the first step that we would want to do is import our new geometry. So what I'm going to do is I'm going to run the flow analysis of the version 2 cooling plate. So to import the geometry, we can simply drag and drop that from the desktop or wherever that geometry is located. And SimScale supports all major CAD file formats, as well as intermediary formats such as STEP or IGES or Parasolid files. We also support proprietary CAD formats as well. So if you've got your data in Creo or NX or SolidWorks, you can import those directly. And we've got an integrated solution with Onshape. So if you're using a cloud CAD provider like Onshape, you can import your CAD directly from there using a plugin in SimScale. So we can launch an Onshape window directly within here. Okay, so this brings in our version 2 of the geometry. We can see the cooling channels that we've got here that we analyzed in the thermal analysis. And we could create a simulation from scratch directly from here. And for this flow analysis, my preference would be to use the subsonic analysis type, because this is excellent for internal flow, and it gives us a very high fidelity solution. But I'm actually not going to do it in that way, because I want to show you how we could use one of these existing simulations as a template. So I'm going to duplicate the version 1 flow, and I'm going to use this as a template for our version 2 flow analysis. So I'm happy with the settings that were used, and then I select the new geometry that was imported into SimScale. And one of the fantastic things about the way we manage the CAD in SimScale is associativity between different designs. So long as the faces are named correctly, the CAD can be completely different. So we've gone from this CAD, which was a completely different CAD file, to this one, but we've maintained the naming convention between the inlets and the outlets and the different faces that we want to assign boundary conditions to. So my simulation is actually ready to go after just changing the CAD. I can immediately run a new simulation, and then in a matter of seconds, I've swapped out the CAD and I'm analyzing a new geometry here in SimScale. I don't have to reassign the inlet and the outlet. I don't have to reassign my result control items for my pressure drop or worry about the mesh. Everything is sorted out for us from that previous simulation that we used. But I've started one simulation, but actually I do want to make a change to this because we saw that there was much lower flow velocity in these right-hand side channels. So as a designer now, I might want to run a design study to really understand how I can optimize this design to effectively cool the cooling plate. So one way that I could investigate that would be to run a design study here in SimScale. So rather than just running an individual flow rate, I could set up many flow rates to be run in parallel. And these can be linear, like 0.1, 0.2, 0.3, or non-linear. I can put in any values I like in here for the flow rate. And SimScale will then recognize that we've got a parameterized study with those different flow rates, and then I can set off another series of simulations in parallel. So V2 parameter study. So these are going to be solved in parallel with that version 2 single flow velocity simulation. And the beauty of all of this being done in the cloud on SimScale servers is that there's nothing for you to have running on your machine. Your machine is now free to do your normal daily tasks. I can close down my browser and I'll get an email notification in around about 4 minutes when all of these simulations complete, and I can come back in and analyze my results once I've been out and had a cup of tea or whatever. So we're now running those in parallel, and just to show you how quickly those results will be available, let's have a look at the previous one I ran. So yeah, that previous subsonic simulation was completed in 4 minutes. So we'd only have to wait a few minutes for all of these to be ready, and then we could analyze the results. But obviously, in the interest of time during the webinar, we're not going to sit here and wait for 4 minutes. So I will switch back to the slides in a moment. But just before I do that, there's another couple of things I want to touch on. So if you need any assistance or you want to ask any questions while you're using SimScale, you can use our in-product chat functionality. So this allows you to talk directly with one of our engineers in SimScale, and you can ask any questions about your setup. So how do I set up a boundary condition, for example? And this goes to real engineers. This isn't a bot. This is manned by people in SimScale, and typically our response time at the moment and during normal business hours is a few minutes. Also, if you tick this share with support, then they actually have access to the project and they can come in and give you some advice and help actually looking at your real simulation project. So you can see here, Guillermo is already responding to us to help us out. The other great way of sharing projects in SimScale is the internal way of sharing projects. So in my previous role, I worked for one of the traditional simulation companies. And if you wanted to share a project, it was extremely difficult over large distances because you had to share gigabytes of data. With SimScale, everything is running in the cloud. All the data is in the cloud. So to share a project, all you need to do is put their email or their username in here, and then they can access, with the privileges that you give them, the project that you're working on. So I could say whether they can view, copy, or edit the project. And then they can immediately come in here, have a look at what we've been doing, and collaborate with us on the simulation. Okay, so you can see our simulations are coming along nicely. 45% through the first one that I ran 3 minutes ago, and the design study is 7% of the way through, so they're going to complete very soon. Okay, so I'm just going to switch back to the slides now to have a look at some results. Okay, so what have we done? I've just done quite a lot there in SimScale, so I want to take a minute to just summarize what we've gone through. So when we analyzed the version 1 versus the version 2 design, we found that despite creating a much higher surface area, we didn't have as good thermal performance. So in order to help understand this, we looked at the flow between the two designs. So we identified that version 2 had flow regions that were close to 0 meters per second velocity in the areas where the peak temperatures were observed. And one of the things that we didn't see in the actual simulation, if it completed, was that version 2 actually has a much lower pressure drop. So it does actually maybe have some benefits there because it's got roughly a 10 times lower pressure drop than version 1. So it's less restrictive. We would need less pump power to actually run it at the same flow rate. So the design engineer at this point might benefit from that design study that we ran with different flow rates. So if we do that, we could have a look at a higher mass flow rate for version 2. And I've done this, and at around 0.3 kilograms per second, we get still a lower pressure drop than version 1. So version 1 had a pressure drop of almost 300 kilopascals. Version 2 would come out at about 100 kilopascals. So still 60% lower than the original design. And if we run the thermal analysis again at that flow rate, we actually see that version 2 performs fairly well. It's not as uniformly chilled, but the average temperature is a lot lower than the original design. So we would obviously need to have further design iterations to converge on a final design. But there, in a very short period of time, we've been able to improve this theoretical design that the designer came up with. Okay, so in summary, what have we done? We've run some heat transfer and fluid flow rapid design checks at an early stage in the design process with no need to have hardware or software maintained on my machine. We've quickly iterated on design changes by swapping out CAD, completely different CAD geometries, and we can run a simulation in a matter of seconds. And we've run a parameter study with, could have been over 20 simulations, it could have been any number of simulations run in parallel. And we've collaborated internally and been able to create simulation templates that other engineers and designers can make use of to increase their productivity. Okay, so that's everything that I had planned to run through. Have we had any questions come in, Paul?
Steve, thank you very much. Yeah, we've had a few questions come in from the audience, and I think we have just 4 or 5 minutes left. So if that's okay with you, Steve, I'll go ahead and just pick out a couple and see how that goes, see if any more. And yeah, please continue to type your questions in. So let's have a look here. Okay, so what turbulence model is used for the fluid flow?
Yeah, so for this particular simulation, we used the k-omega turbulence model, and that can be selected for the analysis that you're running. So we've got various turbulence models available, and certainly if you're interested in running a specific simulation, I definitely recommend that you reach out to our sales team, and we can have a discussion with you about what you would like to run, and we could make some recommendations for the specific turbulence model for your design.
Lovely, thank you, Steve. Okay, a little bit about the hardware. The person's asking about, we mentioned about parallel processing. How many cores can the solver access? So what do they have access to?
Yeah, so that's a good question. So SimScale is running on Amazon Web Services. Computing power. It's all located in Europe, so the carbon footprint of that is good for cloud computing, and we can use up to 96 core machines for the simulations. So and that's all done automatically, because obviously it's not always the most efficient thing to take a small simulation, split it up into many different chunks to run it on a 96 core machine. There's always a crossover point where it becomes more efficient to run on a larger machine. So in SimScale, we take care of all of that HPC orchestration in the background. All you need to do is set up your simulation, hit run. You can leave the settings on automatic, and we will decide in the background what machine it is best to run your simulation on. There's a new virtual machine started in the cloud, and then your simulation will run on the optimum machine. You can also choose the number of cores that you want to use, but we find it's best to just leave it on the automatic setting.
Steve, thank you very much. I think we have time for maybe one more question. Goodness, which one to pick? Okay, can you also, okay, so there's a question here about obviously the heat transfer there's conduction, convection, and so forth. But the question is, can you also factor in radiation heat transfer?
Yes, yeah, you can. So you can take radiation into account for your CHT simulations as well. So that's all taken care of. We usually find it's best to start without radiation, start with the simplest possible simulation setup, and then gradually add complexity to your simulation to hone in on the most accurate possible result.
Steve, thank you very much. Okay, so we just have a couple of minutes left. Let's move on to the last slide.
There we go.
Thanks, Steve. So once again, thank you everyone for joining us today. Now that you've seen Steve's excellent demo, participated in the webinar, we'd like to see how we can get you running on the SimScale platform, assuming you're interested. So basically, you can request a demo, a one-on-one demo, using the link in this slide, or send us an email, and we'll get back to you typically within a business day. We'll also email you a link to the recording for this webinar when it's finished, and you can watch it again. You can share it with your colleagues, etc. And just wanted to say thank you very much again for joining us today, and we very much hope to see you on the SimScale platform soon. So with that, have a most excellent rest of your day.
Thanks everyone. Thanks Paul. Bye.
Bye-bye. Thank you. Thanks everyone.